Okay, well, we have a healthy crowd coming up on 40 here, so let's go ahead and get started. So for this month's installment of the Exoplanetary Solar System Synergy chats or talks, we're pleased to have Johanna Teske. She received her PhD from Steward Observatory in 2014 and is now a staff scientist at the Carnegie Institute of Washington. And she's was the co-PI of the JWST guest observer program that got the most time for exoplanets. So she's going to tell us about their exciting GEO program and also give a summary of some of the other GEO programs that have been selected. So we have a good understanding of sort of what the overall space of what JWST is going to do for us for exoplanets. So go ahead and take it away, Joanne.
Okay, thanks. All right, so you should see my first slide. Good morning or afternoon, depending on where you are, everyone. Thanks for joining. Yeah, so Mark asked me if I would take some time to review what exoplanetary programs had been selected as part of the JWST.
Sorry, Johanna, I'm not seeing your slides yet.
Oh, maybe I have to actually share my screen. Let's try that. I was seeing my slide. There we go. Now, can you see the first slide?
Yes.
Excellent. Okay. So yeah, I just put in this little movie that Goddard actually produced recently. I guess this was like the last unfurling of the mirror of JWST. So I just thought this was really exciting. So I'll review today some of the programs that have been selected as part of the exoplanets and disks category in the Cycle 1 guest investigator program or guest observer program. I've mostly taken a breadth versus depth approach since the publicly available information for all the programs is somewhat limited, except I'll go into a little bit more detail for my program, and then I can add more at the end if people are interested. And I tried to cover as many programs as I could. So if I didn't get yours or someone that you know, it's not, obviously all these programs got selected for JWST time, but I don't have infinite time in the presentation. So I tried to do a broad overview. Oops, let's click this. All right, so first, I just wanted to give everyone, including myself, oriented with the different observing modes of JWST. So first we have these imaging modes. So there's MIRI, and I'll be using these abbreviations, which provides broadband imaging at the longest wavelengths in 9 filters from 5.6 to a little bit more than 25 microns. It offers limited time series imaging. Then there's NIRCam, which has 2 parallel modes, and you can see that in this picture down here. And with each module, the light is split by a dichroic and sent to a short wavelength, 0.6 to 2.3 microns, and a long wavelength, 2.4 to 5 micron channel. Each channel has a comprehensive set of different filters, and it's also capable of time series imaging in both the short and long wavelength channels at the same time. And then there's NIRIS, which is capable of imaging from 0.8 to 5 microns. NIRCam is sort of the preferred choice for near-infrared imaging since it has twice the field of view of NIRIS and has those long and short wavelength channels simultaneously, but used in parallel with NIRCam, NIRIS can increase the field of view and efficiency of imaging. I don't think any of the exoplanet programs used the NIRIS imaging. Then there's these high contrast chronographic imaging that's available between 2 and 25 microns with a variety of chronographs. MIRI has this Leo type chronograph and three 4-quadrant phase mask chronographs. So this provides high contrast imaging between 10 to 23 microns. And the inner working angles of these chronographs range from 0.34 to 2.16 arc seconds, reaching contrast of 10 to the -6 to 10 to the negative, 10 to the -5. And then NIRCam also has 5 chronographic masks, occulting masks, in the focal plane and 2 LEO stops in the pupil plane. And these coronagraphs are expected to reach contrast ratios of about the same as MIRI at a source separation of about 1 arcsecond. Then there's also something even a little bit fancier. NIRISS provides JWST's highest resolution imaging and 4 filters between 2.8 and 4.8 microns using aperture masking interferometry. And this is enabled by non-redundant aperture masking in the NIRISS pupil, which turns the full aperture of the telescope into an interferometric array. And this is really designed to detect point sources at very small, like 0.1 arcsecond separations. There might be a program or two that uses that mode in the exoplanet category. All right, oops, keep clicking the wrong thing. Oh, can you still see my screen? Yes, okay, I think so. All right, then we have the spectroscopic modes, which are even more extensive. So both MIRI and NIRSpec contain integral field units for observing 3-dimensional integral field spectroscopy with wavelength along one axis and sky position along the other 2 axes. So this uses an image slicer design in which the field of view is sliced into multiple long slits, each of which is re-imaged on a different location in the detector. And these have various wavelength ranges. You can see here is like the IFU line at the top, corresponding to MIRI and NIRSpec. All the instruments have spectroscopic modes optimized for observations of single targets, kind of this line and this line. Some of these are intended for time series observations of bright targets like exoplanet transit spectroscopy, while others, optimize sensitivity for fainter sources. So there's MIRI, which has a low resolution spectrometer. So that's MIRI LRS. And this provides single object long slit and slitless spectroscopy from 5 to 12 microns. The NIRCam GRISM can be used with time series spectroscopy for very bright targets. And then NIRISS is equipped with this mode called single object slitless spectroscopy, or SOS, for time series spectroscopy. NIRSpec is equipped with fixed slits and this large square aperture, which can be used for also the bright object time series spectroscopy, or BOTS. And I should have mentioned, just because you might see these abbreviations, the MIRI IFU mode is called MIRI MRS, or medium resolution spectroscopy. And then I think NIRSpec is just called the IFU mode. Then there's a couple other spectroscopy modes, a wide field slitless spectroscopy, and then also NIRSpec has this multi-object MOS spectroscopy mode with a micro shutter array, which is kind of cool, but I don't think any of the exoplanet programs use that. So I won't go into detail about that. All right, I keep clicking the wrong thing. All right, so getting to the science. In reading the program summaries, I sort of grouped them into these categories, which follow a rough timeline of planet formation evolution. I didn't know exactly where to put debris disks because they kind of can happen at many different places. They're just found around a wide range of stars. So I have one slide with those, but then there are a few others sprinkled in at other points in the timeline. So starting with the protoplanetary disks, several programs are really complementing or providing synergy with ALMA observations. Ultimately, with the motivation that ultimately the chemical makeup of disks determines the reservoirs out of which planets form, and therefore their compositions. So there's this treasury program, the D-Sharp MIRI Treasury Survey of Chemistry in Planet Forming Regions, PI by Kala Salik and Klaus Pontoppidan. And D-Sharp was a deep, high-resolution survey using ALMA of 20 nearby bright, large protoplanetary disks, and I'll show a picture of those results in a second, really designed to assess the prevalence and locations and sizes of small scale substructures in the disks and how they might be related to the planet formation process. So this JWST program is going to obtain MIRI MRS spectra of that complete sample and produce gas phase inventories, and radial abundance profiles of molecules in the terrestrial planet forming region. So kind of the several AU region of these disks, really creating the potential to study how global disk evolution and planet formation are interconnected with disk chemistry. And the team, because it's this treasury program, is going to produce and release several higher level data products to the community, including line fluxes, bulk molecular parameters, and molecular abundance ratios. There's also a slightly smaller program by Karin Oberg, but has some of the same goals, called The Chemistry of Planet Formation, a JWST ALMA survey of 4 planet forming disks. This next program I have listed is by PI by Ilaria Pascucci, and that's focusing on transition disks, which are disks with large dust gaps or cavities from a few to tens of AU, and based on spectrally resolved 2.8 micron neon doubly ionized profiles. Several of them have been found, several of these disks have been found to drive slow winds compatible with star-driven photoevaporative flows. But the line profiles can't exclude a different mechanism, magnetohydrodynamic winds, which might not drive disk dispersal, but would drive disk evolution. So regardless of whether these gaps are created by planets or photoevaporation, these transition disk systems are sort of in this unique stage of dispersing their disks. And so this program is going to use MIRI MRS to observe that neon feature in 2 transition disks with large dust cavities and small inner disks, plus already this evidence for a slow wind. And this is the only instrument, MIRI, with the medium resolution spectroscopy that can spatially resolve this emission to near or exterior to the cavity radius. And so it's going to help them distinguish between these two mechanisms that are influencing the dispersal of the disk. And Catherine Espaye also has a similar program. And then this last one that I have highlighted is PI'd by Klaus Pontoppidan, and this is using deep MIRI spectroscopy of 3 volatile-rich protoplanetary disks that we already know show very bright water emission from Spitzer. And this is, again, kind of tracing this 1 AU region. And they're going to search for rare molecules, including heavy isotopologues of water and important carriers of nitrogen and carbon. And so one of the questions they're interested in this proposal is oxygen enriched in heavier isotopologues as seen in primitive solar system material. And so also they can use these observations to search for the effects of selective photodissociation of carbon monoxide, followed by water formation, which has been proposed to explain the strong oxygen isotope anomaly observed in solar system bodies. So this, I thought, was really cool because it's connecting processes that we think maybe are happening in the solar system, or trying to learn more about those by studying protoplanetary disks around other stars. There's also lots of other protoplanetary disk proposals. Ilse Cleves is leading one to look at water, all water ice in the wider regions of the disk. There's another proposal that's using water to trace pebble delivery into the rocky planet formation regions of the disk. And then there's a proposal that is studying or focusing on this dust settling and grain evolution process in edge-on protoplanetary disks. So there'll be lots to learn about this early stage of planet formation from JWST. I didn't want to forget about debris disks. So just Also wanted to highlight two programs that are focused on those. One called Icy Kuiper Belts in exoplanetary systems. And so this is focusing on observations of 4 nearby debris disks using the NIRSpec IFU. These are spatially extended disks that already have surface brightnesses measured from HST and NICMOS and ALMA CO emission. So they think that there's volatile-rich planetesimals in these disks, maybe similar to comets and Kuiper belt objects in the solar system. And so they are looking to search for solid state reflectance features in sort of the near infrared region, maybe from volatile ices like from water, and then constrain the dust grain properties from solid state features and the scattered light. And then the second program is the search for near infrared gas and debris disks. Is there a water delivery mechanism? And this is using NIRSpec with a fixed slit, medium resolution observations to look for volatiles in a sample of 5 debris disks known to have gas from millimeter and optical observations. And this program will particularly focus on the 4.5 to 5 micron water features that aren't observable from the ground. So kind of, again, there's a little bit of a connection to the solar system with these programs, and especially focused on the delivery of, or the distribution of ices and water in these disks. Oops. All right, moving on to proposals that were also about disks, but focused on potential planets forming in them. My impression is that there's still this kind of chicken and egg question, like what comes first, gaps and cavities or planets? How are they related? So the left figure here is these D-sharp ALMA results. And this right figure is a movie from Jehan, who's a postdoc at EPL, which is just showing a numerical simulation with a Jupiter mass planet, the little bright dot here, in the disk around a solar mass star. And the planet opens a deep gap around its orbit, but also additional gaps. And so again, this is getting to the, is every gap, due to a planet, or what's the connection there? So these programs include detecting a young 2 Jupiter mass planet embedded in the disk of HD 163296, which will image this planet in this embedded planet in the disk using MIRI in chronographic mode. This planet has been detected in several independent studies. And in particular, this mode at 11.4 microns is the only available option, they say, to detect such embedded objects for decades to come because of the mid-infrared high contrast capabilities. There's also several other programs trying to detect embedded planets from Sasha Hinckley and others. And let's see. Yes, I also wanted to mention a couple of proposals focused on planetary mass companions and trying to search for disks around those. So these are, I think, objects that have something like 20 Jupiter masses or less. And there are theoretical studies or reasons to expect disks around these objects. And also there's been indirect evidence for disks from optical and infrared emission. And so there's one program that's PI'd, actually has several PIs that's using MIRI and MIRIS to try to observe a disk around this young planetary mass companion, CT Choppy. And then Yalin Wu and Brendan Bowler are leading a program with JWST MIRI to survey planetary mass companions, around seven of these that have comparable masses and accretion signatures. Again, trying to look for disks around these objects and try to model their spectral energy distributions between 5 and 21 microns. All right. There were also a few programs looking at young planets, not necessarily in disks, I think. So there was this one, direct imaging spectroscopy of 2 Jovian exoplanets, characterizing TYC, blah, blah, blah. And this is the most recently discovered imaged multi-planet system containing 2 young Jovian exoplanets at about 160 and 320 AU around a 17 million-year-old solar type star, and they were detected with SPHERE. So that's the publication here. And this team is going to use near-spec IFU and MIRI LRS to obtain complete spectra of both planets from 1 to 12 microns at low resolution. And then at high resolution from 3 to 5 microns, looking at measuring elemental abundances, non-equilibrium chemistry, cloud properties, and trying to constrain the temperatures and radii and metallicities and all sorts of properties of these, and then being able to use those to compare to other cooler planets, other directly imaged planets, and young field brown dwarfs. So this is a pretty cool, very new system and program. Then the other one I wanted to highlight was from Andrew Mann, the atmosphere of a 17 million-year-old hot Jupiter. And so this is using JWST near-spec transmission spectra of this recently discovered young hot Jupiter, HIP 67. Oh, I think I have a movie too. Yes, 6752b. And then, yeah, they say this can be compared to all the existing and planned JWST data on older analogs of this type of object to compare to features seen in more mature hot Jupiter planets. So that's pretty cool. And then moving on to those more mature planetary systems. So starting first with hot Jupiters, there are a couple of programs looking at this canonical hot Jupiter, HD 189733b. So the first one that I just listed is by Drake Deming, and this is measuring the transmission spectrum of this planet from 2.4 to 20 microns. So this contains lots of different features, including like minor species like ammonia and HCN. And so they want to constrain lots of different elemental abundances and see whether this planet is consistent with the solar system mass metallicity relation for giant planets or not. There's also a program by Min et al. To use MIRI LRS to really focus on that detecting aerosols in the atmosphere of this planet. And then there's also a proposal by Kilpatrick and Kataria using MIRI LRS to get an eclipse map of this planet from 6 to 12 microns. So this is an observational technique that measures the exoplanet's thermal structure as both a function of latitude and longitude. And so it yields a 2-dimensional map of the planet's day side. And these will be, this multi-wavelength eclipse map is really going to be very useful for modeling and understanding the planet's 3-dimensional dynamics and thermal structure. So that'll be pretty cool. Lots of focus on this well-known system. There's also several proposals on the system HD 80606b, which is a very high eccentricity planet. That's what this is showing. A large planet, but it has this weird orbit that means it has this very dramatic increase in insolation and tidal forcing as it's passing close to the star. And so in this blast from the past proposal, they're going to observe the atmosphere during that passage, which they call a flashing event, and use MIRI LRS to do that. And then there's another program by Sakura with near-spec bots, so more like 3 to 5 microns, to also observe the eclipse and periapse passage. So we'll have kind of a wide suite of wavelength observations of this target as it passes close to its star. Oops. And then there's this proposal from Hannah Wakeford, good vibrations, directly measuring exoplanet aerosol compositions with MIRI. And so this is focused on another well-known hot Jupiter, HD 209458b. And this proposal is really focusing in on something that is both interesting, but also can cause problems for the interpretation of observations, the effect of these aerosols, which scatter the UV optical light and can mute gas phase abundances in near infrared for transmission spectra. So it can mean that we don't have as good of an idea of what the composition of the planet's atmosphere is. And so in this proposal, they're going to measure, or the objective is to measure the first direct evidence of aerosols by observing the vibrational mode absorption from sub-micron size particles. And from this, they should be able to constrain the particle size and the magnitude of dynamical mixing in the atmosphere to produce those particle sizes. So I thought that was a really cool proposal. There's also, many other like ultra hot planet proposals. There is a proposal from Nestor Espinosa to explore the morning and evening limbs of a transiting exoplanet, trying to get at the assumption that those are, that the terminator regions are homogeneous and seeing if that is actually a good assumption. And then I did also just want to mention Jonathan Fortney and Mark have theory proposals that are going to help us better interpret the atmospheres of both hot giant planets and cool giant planets and brown dwarfs. So those will also be really useful. And complementary, kind of matching the observations, but then also learning from them. That's what Jonathan's abstract talked about, at least. All right, getting to the smaller planets. I sort of grouped these into a couple different sub bins, and the first one was hot rocks. And so Laura Kreidberg has a proposal to observe this planet that she published with Spitzer and found evidence of really no atmosphere with the phase curve of LHS 3844. But she's gonna get more observations with MIRI LRS. There are a couple proposals about 55 Cancri E, which I think this artist rendition is of. Again, trying to distinguish, for example, a scenario where the planet has a thick atmosphere versus a mineral atmosphere, and using emission spectroscopy, secondary eclipses. And then there are a couple other hot rocks, K2-141b, which there's a program led by Nestor Espinosa, transmission spectroscopy with near-spec bots again. And a second proposal on this planet, which will be 3 complete orbits of the planet with MIRI LRS, so a phase curve. And then there was this planet that I missed, or I don't know, I didn't really know about, GJ367b, which is a sub-Earth planet. It has a radius of 0.72 Earth radii. And so the proposers say this is likely the most observationally favorable sub-Earth outside the solar system, and really the only one accessible to study with JWST. And so they'll get a phase curve to constrain the planet's day side and night side temperatures and see if there's an offset in that. Try to measure the albedo of the planet. So that'll be kind of cool. Or I guess hot. Oops. Then there are lots of proposals about this category of planets, super Earths and sub-Neptunes. The other large proposal, the other large exoplanet proposal is being led by Kevin Stevenson and Jacob Luster-Jager. Tell me how I'm supposed to breathe with no air, measuring the prevalence and diversity of M-dwarf planet atmospheres. So that'll be transmission spectroscopy of, I think, 9, their abstract said, terrestrial planets orbiting the nearest M-dwarfs. Hopefully you can't hear that, someone's mowing outside. I'll come back to our program, but I just wanted to highlight some of the other super Earth sub-Neptune programs, one of which is, again, this canonical object GJ1214b. That'll get a full orbit phase curve with MIRI LRS to really try to unlock really what's happening in this planet. The HST spectrum is just very flat, and so they think by getting these thermal emission and observations, they should be able to better reveal the composition of the planet's atmosphere. which they know already has aerosols in it. There's this multi-planet system, TOI 178, and this proposal by Matthew Hooton will get, I think, transmission spectroscopy of planets B, D, and G. So that's really cool, comparative planetology within the same system. Then you can know that the host star is held constant, and just look at what might be happening within that within the system to cause potentially different compositions. And then there are, lots of other ones. Like I said, LHS 114b. There are a couple of proposals for K2-18b, which was this planet that had water detected by HST. And then LTT 1445a is also a target actually in our proposal, and I think Kevin's. It's a very nearby M-dwarf planet hosting system. And so Zach Berger-Thompson is going to get emission observations of this planet for the day side to determine whether or not it has an atmosphere. And our program and maybe Kevin's program will get the transmission spectroscopy. So that'll be a well-characterized super Earth system. Right, and so that's our program, seeing the forest and the trees, unveiling small planet atmospheres with a population level framework, but I'll come back to that one. Then there are several proposals just about the TRAPPIST-1 system. Laura Kreiberg is observing TRAPPIST-1c, which is a terrestrial exoplanet with a temperature similar to that of Venus. And so they'll measure the thermal emission with MIRI imaging to try to distinguish between a bare rock and a planet with a Venus-like composition. There's another TRAPPIST-1c proposal using the near-spec prism to, I think, get transmission spectroscopy, but of the same planets. That'll also be one with a lot of observations. And then Olivia Lim has this kind of catch-all proposal for TRAPPIST-1 atmospheric reconnaissance of the planets. And so it's a bunch of different combinations of instruments of several different planets. My impression was just trying to fill in where the GTO programs were not getting observations of the planets. So we're going to have a really great picture of the TRAPPIST-1 system in the next couple of years. Olivia Lim's program also has a focus on characterizing and assessing the level of stellar contamination caused by the transit light source effect. So, a variable stellar surface, how that can impact the transmission observations. So that'll be important for interpreting all the planets' spectra. Oops. Then the final small planet category is the super puffs, and these are a distinct class of low mass but slightly higher radius planets that they suggest these large mass fractions of gas suggest they formed at larger semi-major axes, but then migrated to their current relatively short period locations to where we observe them today. But that also means they're vulnerable to atmospheric loss, which makes their existence, the fact that they exist at all and have these large gas mass fractions is weird. A possible solution is that they're just enshrouded in high altitude haze layers that make them look bigger than they would if they had clear atmospheres. And so there are two programs to actually observe two different super puff planets in the same system, the Kepler-51 system. So Peter Gao will get transmission spectroscopy of Kepler-51b from 0.6 to 5.3 microns. And then Jessica Libby Roberts and Zach Berger-Thompson will get transmission spectroscopy of Kepler-51d. So this should give us some insight into, in fact, both of them use the word unveiling into the atmospheres of these kind of odd, seems like rare objects. All right. Finally, planets more towards their end of their lives. We have a couple of programs focused on planets or planetary systems around white dwarfs. So these first two are about this transiting planet around a white dwarf. It's a giant planet about the size of Jupiter. and orbits really, really close to a white dwarf star. So this was just detected by Andrew Vandenberg, and he and also Ryan McDonald have JWST programs. I think Andrew's is for a thermal emission spectrum of the planet, and then Ryan McDonald's is for atmospheric transmission of the same object. So this is just a very weird object. We don't know very much about it, and so JWST will at least start to give us some insight into what its composition is. And then there's a program to actually search for giant planets around white dwarfs. These would not be analogous to this transiting candidate in this third program. It's more planets that are on longer orbits, kind of forming beyond the ice line. And this search for giant planets program is targeting 4 white dwarfs, the nearest and youngest, to try to probe down to sub-Jovian masses around these stars. And then this last one is sort of interesting. This is a polluted white dwarf hosting planetary debris, experiencing an infrared outburst on a scale unprecedented in decades of observations. And so they want to figure out what's going on using photometric monitoring and spectroscopy to follow up the system. All right, so that was a very quick overview of the range of other programs. I'll finish by just going a little bit more into the program that Natasha and I are leading. So that was really motivated or inspired by this radial velocity survey that I'm conducting with Sharon Wang and Angie Wolfgang, called the Magellan Test Survey, which aims to address some previous potential biases in exoplanet mass radius studies and investigate the formation of small planets in a robust way. So we're trying to combine quantitative target selection and a quantitative RV observing scheme, and combining that with a hierarchical Bayesian framework to be able to use our sample to say something more broadly about super Earths and sub-Neptunes as a population. So that's just based on masses and radii. Clearly, a critical component to understanding formation and evolution of these small planets is going to be in their atmospheres, which can have different origins, as shown here from this nice figure from Kite and Barnett. So these planets can have primary atmospheres, accreted initially from the nebula, secondary atmospheres of perhaps more varied compositions, outgassed later from the interior. But recent theoretical studies like this one have suggested that both super Earths, kind of 1 to 1.6 Earth radii planets, and the sub-Neptunes, slightly larger ones, might experience interactions between the interior atmosphere and thus give us insight into what's happening inside the planet, which obviously we can't observe directly. So this was something that I was really excited about. And it turned out that some other people were as well. And so motivated by this desire to understand that atmosphere interior interaction, we submitted and had accepted this large JWST GEO program, which will conduct a uniform study of a subset of our Magellan test targets using 3 to 5 micron spectroscopy with near spec and getting transmission spectroscopy. So we have these 4 goals. The first one really is just, and this was actually a goal of Kevin Stevenson's program as well, just what is the probability that a planet at a given radius even has an observable atmosphere? And does that match up to an observable transition between super Earths and sub-Neptunes? We drew, like I said, the planets for our study from the Magellan test sample to ensure that we'll have masses for the planets, which Natasha's work has shown is important for robust retrieval of atmospheric properties. The second goal is kind of going a step further. Okay, for the planets that have atmospheric features, or even the ones that don't, sort of how do we interpret those? Can we start to see any observational evidence of secondary atmospheres through different proportions of these main molecular constituents in the planet atmospheres? And this is really where what helped drive our choice for the type of observations to conduct. By focusing on the 3 to 5 micron range, we're getting contributions from all these different molecules, and also avoiding contributions from kind of aerosols or clouds. So this seemed like the optimal wavelength region, trying to avoid the muting from clouds or aerosols and get the most information. The third goal is pretty simple. Are sibling planets similar or different? I alluded to this in some of the other proposals that have multi-planet systems. 4 of our systems have 2 planets. And so, yeah, we're interested in, do these planets orbiting the same star, but maybe with different insolation fluxes, have different compositions, and what does that depend on? And I should say, TOI 175, one of these planets, I forget which one actually, but one of them is actually a GTO target. So we included the second one in our proposal, and then it's very complementary to the GTO program, trying to make use of other observations that are happening. And then finally, what can we infer about the full population of 1 to 3 Earth radii planets? So after we've conducted the individual planet system analyses, we can then use the results of those in a broader population level analysis, kind of the demographics of small planet atmospheres. And this is, again, leveraging this similar technique that we're using in MTS, this hierarchical Bayesian modeling. But I don't think it has yet been used in a small planet atmosphere, or maybe any exoplanet atmosphere regime, I'm not sure, to really try to explain in a cohesive way a potentially diverse population. So that sort of connects all those other goals and themes, hopefully, into some sort of coherent story, and also then maybe shapes what observational and potentially experimental investigations could follow. So depending on what we find with the non-detections or detections, that can then lead us to what observations might be most useful next, like optical observations to measure the scattering slope, or emission spectroscopy to detect the day sides of these planets. So I think now is, for me, kind of the golden age of super Earths and sub-Neptunes, and I'm really excited to see what we can learn about these planets' atmospheres. And they just represent this like missing piece in the story of planet formation. We don't have anything like this in our solar system. So I think by combining the great capabilities of JWST with our statistical framework, we're going to make a big step towards understanding these atmospheres as a population. So with that, I'll just end by saying that reading through these, I think 70 selected GEO proposals had made me so excited for all the amazing science that is coming our way in the next few years, and reminded me to give thanks often for all the folks who worked on and will continue to work on JWST to make that science possible. So with that, I'll end and take any questions. Thanks.
Thanks so much, Johanna. That was a great whirlwind overview. Above and beyond anything I expected. So that was really useful.
I should mention there's also GTO and ERS programs that I didn't even cover in this. So I encourage folks to go check those out too.
That's right. Just do you have an idea for the approximate number of planets there are? What would be your guess if you added them all?
Kind of covered across all the different programs? Yeah. I don't know offhand. There are a few that overlap, but probably something in the like 30 to 50 range. I think, if maybe you also include kind of those potential embedded planets.
Avi says in the chat it's about 65 or so.
Oh, okay. I wasn't too off.
If you have any questions, why don't you raise your hand and I'll call on you and you can unmute yourself. Anybody else? Let's see what we have in the chat. Yeah, Jesse says it's all Nicole Colon worked that out. Let's see. Avi, go ahead. What's your question?
Hey, Joanna, great overview, by the way. Really nice. So wondering about the overlaps between programs. Obviously, you pointed a number of them out yourself. Do you know how the mission or the space telescope or whoever is going to handle all of that?
Yeah, so some of the overlaps are the same target, but a different mode, right? So I assume in that, then there's nothing that they have to change. Our program and Kevin's program, I think, had overlap in the targets and like the observations that we would conduct. So I actually don't know. I would assume that they're not going to do the same observation more than once. But I haven't received any communication about how that will work out. So I'm not actually sure. Maybe that will come when we start doing the scheduling.
Okay. Schwan.
Yeah, thank you, Mark. I have another question. For some reason, I remember there's one proposal will observe TRAPPIST-1G or TRAPPIST-1H, but I didn't see on your slide. I'm now confused. Maybe maybe I remember something wrong. Can you confirm that?
Yes. So I don't remember. So there was the Olivia Lim proposal might have. Let me go back to that because I have it in my notes. Come on. Her proposal may have.
You mean the third one, right? The last one.
Yeah, this last one. Let's see. So yeah, she's observing 8 transits of B, C, G, and H using near spec and nearest. 2 transits of each B and C. So that's, yeah, that was the one where I was like, it's kind of a catch-all, like filling in the gaps where other proposals haven't. So there is at least that one proposal that's doing G and H.
Okay, yeah, thank you.
Sure.
Anybody else? Other questions? Comment from Glenn. There are also GTO observations and associated AR programs for exoplanets in our backyard, Uranus and Neptune. And we have a follow-on GEO programs on Neptune, all with MIRI IFU observations. Yeah, that's great. And also Connor Nixon is the next, a month from now, is going to give the same kind of talk, sort of summarizing the solar system observations, keeping an eye out on what is interesting from the exoplanet perspective, which is what we're really trying to show is this synergy. So thanks for pointing that out, Glenn.
Yeah, good. Thank you. Yeah. I couldn't figure out how to raise my hand.
Any other questions or comments? Okay, well, let's thank again, Johanna, very much. That was really great. I'm going to be lots of people, I'm sure, are going to want to refer to your talk once we get it online. So really, I know that took a lot of work on your part to put that together. So thank you.
You're welcome. It was fun. I mean, like I said, it just made me like super excited for the next 2 years.
Let me just end then on a personal note. I've appreciated everyone who has spoken this series, and it's been a lot of fun taking part in it. On Friday is going to be my last day at NASA Ames, and Natasha is going to be there executing this wonderful program for her part of it. So keep an eye out for the opportunities and postdoc opportunities. And if you have a chance to go work with Natasha at Ames or anyone else, please jump on that. Starting on Monday, I'm going to be taking over directorship of the Lunar and Planetary Lab in Tucson. And one thing I want to do is really grow the opportunities here at the interface of solar system and exoplanet science, and the university is committed to that, and there's going to be new higher opportunities. So please keep an eye on LPL, and when the time comes, apply to come join us. So with that, Laura and Vicky are going to be taking over 100% of the realm. I'm going to step back from my part of this series, and I'll let Laura, since I see her, do you want to say anything for, again, I guess Connor Nixon is next week and beyond, or next month and beyond that?
Right, sorry, Vicky says Connor is speaking June 3rd. June 3rd. Okay. And then we're taking a brief hiatus over the summer. So we will be back in September with tutorial talks after the summer break. So stay tuned.
Okay.
And thank you, Mark, for all your help in getting this started and getting it going. And thank you again, Johanna, for a really great talk on the JWST exoplanet programs.
And to the audience too, if you have suggestions for what you'd like to hear about, we're all ears. So yeah, please let us know.